All right. Excellent. So yesterday we finished off our discussion on the equilibrium constant itself, K. And we did some very preliminary, straightforward calculations. The textbook tried to make it difficult by leaving out the important information of whether what number 2 was at equilibrium or conditions or not. Anyway, that was at number 2. I don't know if anybody realized it, but they gave you 3 concentrations, and you had to assume that they were all equilibrium concentrations in order to actually get the answer. You didn't need an ICE table for that one. You just needed to put it in and find the K. All right. Were there any other concerns or problems with any of those other problems that I gave you, like that they were totally confusing wording, that type of thing, or were they okay? We were okay? We're going okay? All right. Excellent. Again, I haven't looked at each individual problem in the new textbook, so your feedback is going to guide me on what I need to do for that. All right. So what we want to talk about today and tomorrow is starting from initial conditions, starting from something other than equilibrium. In yesterday's problems, we just said, hey, if it's at equilibrium and these are the concentrations, calculate the K. Put it in the equation, get an answer, pretty straightforward. What we want to deal with today is, what if it isn't at equilibrium conditions? Even that second example we did yesterday, we were giving you the I's, and then we gave you one E, and it was really easy to find the other equilibrium conditions and then solve for K. You might say that that one isn't starting at equilibrium, but in the end, when they give you the E, you can calculate all the rest of the E's and you're done. You've got the number. What we want to talk about today and tomorrow in terms of calculations is, what if it isn't at equilibrium? And you could have 2 scenarios. One scenario, you're doing the experiment, you're setting up the apparatus, you're getting your reactants, you put the reactants in your closed system, whatever that might be, and you tell the reaction to go. Well, you don't really do that, but in my mind when I'm doing the mathematical problems, that's the way I imagine it. We give you the initial conditions and we say, go, react. And then we do some calculations and we figure out all the equilibrium calculations, or we figure out the K. There's all kinds of different ways we can solve it. So we're going to be starting from initial conditions. That's actually the second problems I'm going to do today. The first problems deal with a second scenario. Let's say you come into a lab and someone else has been doing a lab, set it up, and you analyze their laboratory equipment, and you measure some concentrations of reactants and products, and then you ask yourself the question, is this system at equilibrium? Is it at equilibrium or isn't it? And that's the first thing we want to cover today. Is a system at equilibrium? So, first question, or first scenario that we're going to deal with is answering the question, is a system at equilibrium? And we're dealing with it mathematically, obviously. And it's actually a very easy method to determine if a system is at equilibrium. We simply calculate the K, and I'm putting K in quotes. We simply calculate the value by putting all of the reactants and products into the equilibrium expression law. We get a number. And then we compare that number, we call it Q, to the value of K. So we're going to calculate something called a reaction quotient. All I've written down here is it at equilibrium? I'm going to fill it out in a moment. This Q, this reaction quotient, is sometimes called a test K. Given whatever numbers we have, we put it into the equilibrium expression, we get a number, and we compare it to the K. It's like a trial K. So the question's going to go like this. Instead of it saying that it is at equilibrium, they'll simply give you three numbers. It'll be kind of like question 2, that everybody was kind of wondering, gee, do I use the I's or do I use the E's? That actually would be not a bad question. Is it at equilibrium? Because they just give you three numbers and they don't tell you whether it's I's or whether it's E's. And so what you do essentially is, you calculate the K, but we can't call it a K because it actually isn't the K value. So we call it Q, a reaction quotient, because really when you think about it, we're doing a division. It's a quotient. And we simply test that value against the K. Is it bigger than it? Is it smaller than it? Or is it equal to it? If that Q is equal to the K, then it's already at equilibrium. The concentrations of the reactants and products are in that balanced state such that it is at equilibrium. They, in fact, gave us E's, but we didn't know that. And if it's not equal to K, then it's not at equilibrium. It means we either have too much product or we have too much reactant, and it's sitting too far to the left or too far to the right, and that reaction will shift to get to equilibrium. A reaction will take place. So how do we calculate Q? Very simply, we make a calculation just like we would any other equilibrium situation. I'm assuming that A and B, I don't know why one is bold and one isn't, not a big deal. We're assuming that A and B are both aqueous or both gases. And don't worry about this little subscript C. That sometimes comes in if we're dealing with concentration data as opposed to gas data. I have not distinguished between it, so I wouldn't even write it down. Don't write that little C down. I wouldn't even bother with it. If you've got it, it's not critical. It's just it's not critical. It's that simple. I don't need to state it again, I guess. So you have a reaction, you're given some data in the question, it doesn't tell you whether they're I's or E's, you have all of the reactants in the products. What do? You do a calculation just like you would to find the K. Keeping in mind, it's not the K. It's like a test K. And then you simply compare it to the K, because they're going to have to give that to you. So you're going to have all the information and the K will be given. So there's our tactic right there. In this case, is it at equilibrium? You'll be given, right, all concentration reactants, and all concentration of products. You'll be given them all. But the question is, are they I's or E's? So in this case, question mark, I's or E's? That's what you don't know. You don't know whether they're all I information or E information. So what do? You calculate Q. Calculate, oops, oh, I'm losing it. Oh, my good piece of paper. Calculate Q, again, just as we normally would. Concentration products over concentration reactants, right? And compare to the K. And you have to be given K, given all reactants and products and K. That's what's going to be given in your question. And they're not going to tell you whether it's I or whether it's E. That's what you've got to figure out. If you find that the Q is equal to the K, they gave you E's. Oh, they gave us the equilibrium concentrations. Okay, we know it is at equilibrium. If it's not equal to K, then they gave you I's. And that reaction will shift to get to equilibrium. And later on in today's class, we'll learn how you then determine which way it's going to shift and what. Actually, we can determine which way it's going to shift. We'll be able to calculate it. Let's now talk about what it means. Now, you'll notice that the Q's equation is just like the K's equation. And therefore, the relationship between Q and products is also direct. But we've got to think of it differently. If a K has a large value, it means at equilibrium there will be a lot of product, right? Make sense? If a Q has a large value, it means that if a Q is larger than K, it means that there's too much product. It's a similar relationship, but the meaning is slightly different, all right? Let's go ahead and write this analysis down for a minute. I've left a blank in there, and you can just leave it blank if you're not sure. If you've got an idea, you can fill it in. We'll talk about it in a moment when you're done writing. So we've been given some numbers. We calculate this Q, just like we would calculate a K. We get a value. They've given us K. We've made a comparison, and we found that the Q is bigger than the K. What does that mean? Well, when we calculate Q, we use the same equation. So just like yesterday, this value of Q is directly proportional to product. All right? Whatever the number is, whether we're talking Q's or K's, the bigger it is, the more product. We're talking about product number high, product number big. If Q is bigger than K, it means we've got a big number on the top and too small of a number on the bottom compared to what it should be for K. It means that the product value is too high. There's too much product in this particular situation. So the reaction must shift blank to reduce the products and therefore reduce the value of Q until it becomes equal to K. Well, we use the term shifting right or left, just like we did yesterday when we learned that an equilibrium either sits to the right or sits to the left. Now we're talking about an equilibrium moving product to reactant or reactant to product to shift a reaction into equilibrium. if there's too much product, just like this big B right here, which way is the equilibrium, or which way is the reaction going to shift in order to get to equilibrium? Which way is it going to shift? Yep, it's going to shift left. It's going to shift left. This is going to reduce the amount of product, increase the amount of reactant. The value of Q will change until it is equal to K, and equilibrium has been established. So we use this mathematical value of Q to see where we're sitting with respect to equilibrium. If the Q is smaller than K, it means, because keep in mind, the Q is related to product. I always think in terms of products. That means product is too low, so the reaction must shift. Which way is it going to shift? Right, to produce more. All right? And increase the product, increase the value of Q until it's equal to K. All right? Just differentiating between what we just did here now and what we did yesterday. The value of K tells you where the equilibrium sits. If K is big, there'll be lots of product at equilibrium. If K is small, there'll be very little product at equilibrium. So it's how much product we have at equilibrium. This Q assumes we're not at equilibrium. And instead of telling it where the equilibrium sits, its value is going to tell us if we've got too much of one thing or too much of another thing, reactant or product. But you can analyze it just like you're thinking about a K. It just means it's going to shift to get to where it needs to go. So if Q is too big, too much product, we've got way too much of this, it's going to shift left until we get to K. And if K is too small, too little bit of product, it's going to shift right until the numbers become K. All right? Let's do some calculations. Again, no need to write this down. You can just, say part A, number 1, I'm hoping it's exactly the same. So this is to save us a little bit of time over the next couple of days so you can have more time to work on practice problems. Let's make sure it's correct, because sometimes when I put this together, I change it, I don't even realize it. So we've got an equilibrium system. They've given us the K. The system was analyzed, and the concentration of the gases were found to be, and I believe those are the gases. And the next question is it at equilibrium? So let's take a look at what information we have. We've got the K. We've got the numbers. It's as if they've given us all the information compared to yesterday. And you know what else? They ask the question, is the system at equilibrium? So these are actually easy to pick out, because normally it asks, is it at equilibrium? And if it's asking you that, calculate a Q. We get Q just like any other regular equilibrium expression calculation. So again, you guys can go ahead of me. Many of you do. That's very good. We're simply starting with the products, with the exponents, concentration of NH3 squared over the concentration of N2, concentration of H2 cubed. Let's just put the numbers in. 2.2 times 10 to the minus 4, all squared. N2 4.0, and that's it, right? And H2 is 2.0 times 10 to the minus 2, and that's cubed. And when you guys have calculated such a thing, I will take the value of Q. John put the calculator down with authority, which means he's got a number. What do you got? 6.875. That's plenty of significant digits. 6.9. At this point, it really is not a concern. Do we like that value? We like that value? Concern? We don't like that value. All right. 2.2 times 10 to the negative 4 brackets squared divided by 4 divided by 2 times 10 to the You know what? We can do a little interesting check here. A good little mathematical trick to know and to learn is to look at the powers of 10. I don't know if I've taught you this. Did I talk about this last year? Yes, no, maybe not. You might learn this in physics. If you look at the powers of 10, you'll know whether you're in the right ballpark. If I just look at the exponent rules, 10 to the negative 4 squared is going to be negative 8, right? And then I'm going to divide off a power of 10, which is 10 to the negative 2 times 3, that's 10 to the negative 6. Negative 8 divided by negative 6 is going to get me negative 2, right? It's going to get me a 10 to the negative 2. This is a number that is essentially 10 to the 0, which is equal to 1. So I should have an answer that is approximately 10 to the negative 2, 0.0 something something. Or it might be off by 1 power of 10. But that's a quick check. Look at your powers of 10. That's 10 to the negative 8. That's 10 to the negative 6. Negative 8 on top, negative 6 on the bottom will cancel out. I'll be in negative 2. We're looking at something around 10 to the negative 2. What do you got? Negative 3? That's okay. 1.5 times 10 to the negative 3. And when I say 10 to the negative 2, I mean close to it. And negative 3 is close. What happened there was, right, this 2 probably cancel out that 2, and then I'm dividing by 4. So I'm making it into like 1/4, which will bring in one more negative exponent. That's where the negative 3 comes from. So that's always a good little check. All right, let's take a look. How do we compare? How is the Q related to the K? That's 10 to the negative 3. This is 1, 2. That's 10 to the negative 2. And therefore, the Q is less than, because 10 to the negative 3 is smaller than 10 to the negative 2. Okay. A little bit of powers of 10 lesson here today along with it. Which means, which way is it sitting? Is it sitting too far one way or too far the other way? Which way is it sitting? It's sitting too far. Which way? Yeah, it's sitting to the left. If Q is too small, it means there's not enough product. There's a very little amount of product, and it's sitting left. So therefore, it's sitting left. In order to get to equilibrium, which way is it going to shift? It's going to shift right. It's going to shift right. And reactant will become product in order to establish equilibrium. Okay? All right, let's do one more. Normally we do 3, one that's too far left, and one that's too far right, and one that's just right. But I got rid of the third one. I can't remember which one the third one was, so here we go. We've got an unknown. We don't know whether it's going to be which. I apologize for my PowerPoint. The font packs vary, and therefore sometimes my degrees turn into, this time it's a hand. Degrees. Right? Like he's some kind of cool dude. 430 Celsius. Yours actually has a degree sign. Same thing, you guys are pretty good. You've probably already done the whole analysis, which is excellent. Concentration of I2, concentration of H2, concentration of HI squared. Now we're going to put in the numbers. H2, I2, 0.010, H2, 0.040, and 0.14, and that's all going to be squared. Again, for a powers of 10 check, if you want to do a quick check to see if you're on the right track, I'm hoping we know this is a 10 to the minus 2, right? In terms of scientific notation. 1, 2. This is also a 10 to the minus 2. 10 to the minus 2 times 10 to the minus 2 is 10 to the minus 4. This is a 10 to the minus 1, but it's squared, which is a 10 to the minus 2. So minus 4 up top, minus 2 down below. They cancel. Again, we're in the minus 2 range. We should have a 10 to the minus 2 approximately, or 10 to the minus 3, right? Or it could be the other way around, 10 to the minus 1. When I say approximately, you're flanking it by 1, depending on what the values of the numbers are. But that's always a good check to see that you've done the math right. Does somebody have an answer for that, for our Q? What do you got? Yep, Christian? Times 10 to the negative 2. So our approximation worked bang on this time. But keep that in mind. You can do a quick check to see if you're unsure, right? If you're sure, your calculator fine, that's great. But if you're unsure, you can always do a quick check. Okay. Oh, look at this one. 1, 2. That's exciting. We're really close. But if we're going to be picky, we will, we'll say they're different. But they are fairly close. 2 times 10 to the minus 2. 1.8 times 10 to the minus 2. It's almost at equilibrium. But it's not there, so let's compare it. Q is what compared to the K? Yep, yeah, it's greater than, which means, where is it sitting? Actually, instead of saying sits, we can say too much. This is another way of saying the same thing. If it's bigger, there's too much what? Yep, there's too much product. Too much product, concentration product. Therefore, shift. Which way is this thing going to shift in order to attain an equilibrium? It's going to shift left. Therefore, shift left. Okay? All right? Maybe too much product is a better way to say that it sits to the right. You can say that as well. We sometimes say, oh, that reaction is sitting too far right. It's going to shift left in order to get to equilibrium. So that's how you tell whether it's at equilibrium. You'll be given all the information and the K, find the Q. And we could actually now start at this point and go ahead and solve a problem. What are the new concentrations going to be at equilibrium? That's the next examples, all right? There are a couple of questions that deal with this that are just determining whether it's at equilibrium or not. But I'm not going to let you work because I'm going to then show you now what to do if it's not at equilibrium. Yep. Yep. To be able to say that it's at equilibrium, for this course, let's put it exactly the same just to make it easy for you guys to analyze, right? So if I want to give you a problem on a test or an assignment, I will make it exactly equal so that you can say it's equal to. Equal using the appropriate number of significant digits, right? So if you follow your significant digits rule properly and you find it's the same, then we'll say it's equal. That's really close, right? Again, to be honest, I've never actually worked in a laboratory where we use equilibrium stuff. You know what I mean? We have many systems that are at equilibrium, and we're going to be using them. But equilibrium is such a thing that you put the reactants in there, and if it's not at equilibrium, it goes to equilibrium as quickly as the reaction rates will allow it. So it's not like we can say, and we do this when we solve problems. In our minds, we say, okay, let's put the reactants in, and then we say, stop, don't react, so I can analyze to see if you're at equilibrium. Just wait for a minute so I can write all the numbers down. That's not what actually takes place, right? As soon as you put the reactants in the vessel, equilibrium starts to become established. It's a natural process. So really, it's difficult to actually come across a situation. It's more of an actual real situation where you'd say, okay, I plan on putting this in the reaction vessel. I plan on doing it. Would it be at equilibrium, or is it going to shift, right? So some of the equilibrium we're going to look at are solubility equilibrium. When something dissolves in something, same thing. As soon as you put that substance in there, if it isn't at equilibrium, it's on its way to becoming at equilibrium until the K is equal to the Q. So I've never done an actual lab where it's like, okay, let's take a look. Is it at equilibrium? Let's measure some stuff, because that's really not a practical thing. Because once you've introduced it into the vessel, it's on its way to going to equilibrium. It just happens. It's just the laws of nature that drive it there. So yeah, it'll be exactly on the money for testing purposes, all right? Okay, so the next question is, all right, if we find it's not at equilibrium, how do we figure out all these equilibrium concentrations? And so that's what our next couple of days are, and there's actually 3 types of questions that we can deal with here, and I'm going to introduce one today. I might even be able to get to the second one, and if I get, no, we'll let you work, and then we'll do the 2 more tomorrow. And these problems are all identical. We start them the same way, but the way we calculate them is different. These 3 different problems that I'm going to go over in the next couple of days are differentiated by the mathematical methods we use to solve them. So this is really more, what math tricks do we use to solve these problems? All the problems will start out the same, but it's the mathematical technique that I'm teaching you. So the first technique that we're going to use is perfect squares. Again, in your examples, you can put down calculations involving perfect squares, but again, I have the examples on the page. And there is a little change up. I don't start with number 1. I'm going to start with number 2. I might come back and do number 1. We'll see. We'll see what the example. So that's example number 2, by the way, if you are following along on the sheet. This is example number 2. Look at that. How far off could I have been? Am I far off there? Oh, it's because I'm up here. I must not have pushed that dot very well. Anyway, not a big deal. This is not the same as number 2. It's number 3. What the dickens am I doing here? Is that number 2? Oh. We'll do number 3 first. Doesn't matter. Number 3. Look at that. Whoa, number 3. We got it. It's number 3 on the sheet. Okay, so we look at the problems. It's looking very similar to all the stuff we've done. We've got an equation. We're given the K, and we're given concentrations initially. So in this case, we're given I's and we're given K's. All right? And I'll write this down in a moment. And so we've done all these, calculating the K, beautiful, calculating just 1, excellent. We've done the equilibrium. And I'll write this down in a moment. But notice we're given all of the I's and we're given the K. And there isn't anything on there, right, that looks anything like this. All the I's and not one E. We're not given any E's, but we're given a K value. Yep. Sorry? What's different about it? You're right. It is different. No, it's different than number 3 as well. It says 4 moles of each gas placed in 1 liter vessel, heated to 700 degrees. We've got the same thing. Determine the equilibrium concentration of the gas. 1 mole of that, 1 mole in that initially placed. Oh, man. I do want to do it this way as well. Jeepers. What do I want to do? Have you guys written anything down yet? What have you written down? I want to know what you've written down so I can make this easier on the people who have issues with using erasers. I'm talking to Jessica and Jenna. What have you written down? That's all you've written down? Excellent. I like it. We're going to this. We'll do number 3. We're doing number 3 just the way it's written there. All right? So you guys are looking at number 3. Is that good? Number 3. Is this going to auto-hide? Get out of the way. Number 3. Okay. So we're given a bunch of information. Better look at my paper. And we're given the K. In these problems, we need full ice tables and we need to solve everything, all right? And these are the full questions that we deal with when dealing with an equilibrium problem. So write down your balanced chemical equation, CO2, and notice they're all gases, so I'm going to leave that out. It's only when they're heterogeneous that I write in what the states are, but these are all the same states and they're all gases. It's going to be one of those days. All right. I can erase here. Woo, this eraser. What? Oh, my goodness. It was letting me erase the other day. Oh, I can move it. That's really not useful in any way. CO. Ignore that. Over there. This is for Miranda when she's watching it. Miranda, just ignore that CO2 in the corner. All right. What do we got? 4 moles of each gas placed in a 1-liter reaction vessel heated to 700 degrees. We should calculate the concentration of, and I'm doing number 3, right? Okay, that's exciting. 4 moles of each gas placed in a 1-liter reaction vessel heated to 700 degrees. We should be calculating the concentration of each of these gases. But notice it's 1 liter. So what's the concentration in moles per liter? 4. All right. So I'm going to just do one calculation off to the side just to kind of illustrate this. But the concentration of all of these things, we'll do CO, is equal to 4.00 moles per 1 liter. Okay? And therefore, it's 4.00 moles per liter. Okay? And that's true for all of the reactants. And notice it said all. That's exciting. That means in my ice table, I'm going to have 4, 4, 4, and 4. Because it said each gas. Now this is hilarious because I don't want to start with this one normally because the question comes up, which way is this equilibrium going to shift? So in other words, where are my negatives going to go and where are my positives going to go? We can actually get that information from the K. Again, off to the side, I normally write the K, but I don't have enough room. I'm going to write it up above, but you just write it off to the side. What is the K value on that? 8.3. 8.3. That doesn't really help us very much because remember, if K is big, there should be a lot of products, and if K is small, there should be very little product. This is kind of close to 1, which means it should be balanced. And you'll notice it's almost balanced right now. Actually, if we were to calculate a Q, which you don't have to do in these problems, because I'm telling you that it's not at equilibrium, but if we were to quickly calculate a Q with everything having a coefficient of 1, what's the Q value there without writing it down? It's equal to, nope, not equal to 0. Yep, it's equal to 1 because it's going to be 4 times 4 divided by 4 divided by 4. So the Q is actually right now equal to 1. Which way is this thing going to shift if the Q right now is equal to 1 and the K is equal to 8.3? Which way is it going to shift? Yep. It's going to shift right, just a little bit. It's not going to move very much. Now that's actually going to help us determine what the sign of the X is. Because if it's going to shift right, this has 1. What am I putting over here? What's happening to my reactant? Is it disappearing or is it appearing? Disappearing. So what should I put here? Negative X. Negative X. Negative X. And on this side, X and X. But as I've stated in the past, let's say you didn't calculate the Q. It wasn't so easy to calculate. And you don't have to calculate for these. If you put the negative on the wrong side, you'll end up with your X value being a negative number. And when you substitute it back in for negative X, the two negatives will cancel away and you will get the right answer. So even if you decide wrong on which way that's going to shift, you will always get the right answer as long as you do all the math correctly. All right? Okay, let's let's finish off by getting our E line. 4.0 minus x, 4.0 minus x, 4.0 plus x, 4.0 plus x. Now at this point, it brings us to a situation where we have nothing to solve for x for. In the past, I've given you one of the e's, and you just simply solve for x and away you go. But we have a secondary equation. We know the equilibrium expression law, and we know what that value is supposed to be equal to. So I can make the statement, K is equal to the concentration of H2 times the concentration of CO2 over the concentration of CO times the concentration of H2O. All right. We know that value, and I just moved that slide away. We know it's equal to 8.3, so I can say that 8.3 is equal to, and now I've got all these great E values with all kinds of X's in them. And now we're doing a lot of algebra. So now it's going to be equal to 4.0 minus X, plus X, 4.0 plus X over 4.0 minus X, 4.0 minus X. And we've got to solve for X. And once we solve for X, we can then put it back in and we can then do everything. Now, looking at this, you might think, uh-oh, we're going to have to FOIL it all out here. We're going to have X's and we're going to have X squareds and we're going to have all kinds of ugly stuff. But this particular question falls under my category of perfect squares. You'll find that we can put these two together, 4.0 plus X squared, because they're the same. And I can do the same on the bottom, 4.0 minus X squared, and that is equal to 8.3. Which means without having to FOIL it all out and get a bunch of X squareds, I can actually now take the square root of the right-hand side because they're both squared. If I take the square root, then that square will disappear, right? I could actually rewrite that as one more little step. If you wanted to see one more step, I could say 8.3 is equal to 4.0 plus X, 4.0 minus X, and the whole thing is squared. Because I have two identical things on the top, two identical things on the bottom, they're squared, I can pull them out. The fact that they're both squared makes this what we call a perfect square problem. And we can solve it by, what am I going to do next mathematically? To get rid of that square, take the square root, all right? So if you're wondering what makes this a perfect square problem, right there, these two things, which then we turn into that, makes it a perfect square problem. And that's what you want to look for. You usually can get a perfect square problem if you've got some symmetry in your initial data. You'll notice the initial data is all the same. And they all have the same coefficient, which means we get the same expressions out, which means we'll end up maybe with a square. That's one way of spotting it. Okay, let's do the math now. Square root, oops, it hates it when I move this thing. Square root. If someone could give me the square root of 8.3 and give it to me to 3 significant digits so that we can round back, because I want to keep an extra digit so I can round back to where I came from. Jess, what do you got? 2.88 equals 4.0 plus X over 4.0 minus X I'm going to bring that bottom bracket to the other side and multiply the 2.88 through. Then I'm going to redistribute and I'm going to solve for x. Usually on the board I'd move it up into this location, but I'm going to continue to just extend the page and work my way down. So 2.88 times 4.0 minus x equals 4.0 plus x. Right? See what I did there? The maneuver was bring that up, multiply it on the other side. Because I know our algebraically challenged would be just a bad thing to say, so I won't. Those of us who don't like mixing numbers and letters are feeling some stress right now. Bringing that through, I need a 2.88 times 4. Somebody have that? Yep. 11.52 minus, and then the 2.88 times the negative x. 2.88x equals 4.0 plus x. Again, mathematically, I'm bringing this over here, making it a negative, right? I'm bringing that over there, making it a positive. So I'm having here 11.52 minus 4.0, and this is x plus 2.88x. I'm hoping, again, algebraically, we're making it. And 1x plus 2.88x equals 3.88x. Again, for those of us who are not very strong in the algebra, in the algebraic arts, if you can say that, you can't. Here's what you can do. If I pull out a common factor of x, then I get 1 plus 2.88, and I know that you know when you hear my little condescending voice, I'm getting into some piddly little math, but again, I want to show those who are not a fan of it, and there it is right there. So I've got then x times 1.88, and that's x then times 3.88, or 3.88x. All right? 11.52 minus 4, what's that? 7.52? Did I do that right? 7.52. I can do the algebra. It's the simple math I have trouble with. And now I'm going to divide off the 3.88. Woo! We're almost there. 3.88. You can feel it. We're almost there. X. What do we got? 1.94? 1.94. All right? And that's just a value x. Okay? So we got to do some algebra here. Moving back to the top. I can now finish the question. What does it ask? Does it ask for the concentration of all of the gases at the end? Right? Therefore, so now I can make a little therefore statement. You'd put it at the bottom. Concentration of CO, which is actually, in this case, equal to the concentration of H2O. So I can kind of double it up there. Is equal to, and I apologize, I've run out of room here, but it is 4.0 minus x, which is 4.0 minus, I forget that number at the bottom, 1.94, 1.94, and therefore the concentration of those two things is 2.06. Let's round back now to 2. So 2.1, 2.1 moles per liter. That's the last step in doing these problems, substituting it back in and then solving it. And we can finish off with the concentration of H2 equals concentration of CO2 equals, and I apologize, I'm out of room, 4.0 plus x, which is equal to 4.0 plus 1.94, which is equal to what? 5.94. 5.94. Where are we rounding that to? 5.94. Rounding to 5.9, right? 5.9 moles per liter. And there's our equilibrium. Oh, that's fun. Fun stuff. Let's do one more example. And let's not worry about example number 1. We'll just do example number 2 on that page. But a little rundown of what we did. We read the question. It tells us initial concentrations. It tells us K. When you're given all the initial concentrations and all the K, you need an ice table. You then need to put it in the equilibrium expression law. And at this point, you're looking for perfect squares. Tomorrow, I'm going to show you what happens if it isn't a perfect square. Okay? So right now, we're looking for a perfect square to make our algebra easy so we didn't have to deal with x's and x squareds. In the end, folks, and those of you who have taken physics and have done math, when you end up with x's and x squareds and numbers, what do you end up having to use eventually? Yeah, the very last one we're going to do tomorrow is nothing else works. None of our shortcuts work. We have to use the quadratic equation. So yes, we get to use the quadratic equation. I hate the quadratic equation, but it's exciting when you get to use it. Okay, let's do number 2. And I'm not going to bother with number 1 because number 1 is actually a solubility problem, and we will see that in the solubility future. Okay, so question number 2 is what? You guys can start. You write the equation down, you fill in your data in the ice table, and you fill out an ice table, right? Because again, we've got 1 mole HI in a 1 liter vessel, and that's it. This one's looking nice and easy compared to the last one. 2 HI, again, they're all gases, so I'm going to just leave that out. H2, I2. You'll notice we use the same reactions over and over again. And that's because we're not worried about the reactions, we're worried about the math now. We want you to be able to do the math. 1 mole in each one, 1 mole of HI in a 1 liter vessel, that's 1 mole per liter, right? And that's the initial, right? It was placed in there and allowed to reach equilibrium. So that's HI, which means I only have a 1 in there. And what are the other 2 values? 0, because it just said that there was only HI. 0, 0. This one's easy. It has only one choice to shift a certain direction. Which way is this thing going to shift? It's going to shift right. There is no product. So it has to shift right. Minus 2x, x, x. Oh, I should write down the K. What is it? 1.0184. 0.0184 is equal to K. Notice we give you the temperatures, but we never actually use the temperature values. That's because the K is only true at a certain temperature. We'll learn in the future what happens when the temperature changes, but we don't really need to worry about temperatures ever in the questions. They just need to be given that it's a constant temperature. Add your things up. 1.0 minus 2x, x, x. That's looking like fun. You might think, oh, this isn't looking nearly as symmetrical as the last one. Let's hope it works out. It's a perfect square. So if you're good to the point where you can go right to writing down the number equals and putting in the x values without writing down the equilibrium expression law, because you've practiced a million times, I don't mind that. I'm going to write it down again, though. K is equal to the concentration of H2, concentration of I2, concentration of HI squared. Let's put our information in. 0.0184 equals x, x, 1.0 minus 2x, and that's all squared. And when you're at this point, you're desperately looking for a perfect square. What can I do? What's true here about my statement that I can fix up and clean up here and maybe make it into a perfect square? What can I do? Somebody tell me. Yep, Ryan? Yep. So 0.0184 equals x squared over 1.0 minus 2x squared. Got a square on the top, square on the bottom. Now you could rewrite, right? You could rewrite, but we don't have to. What can I do with this if it's a square on the top and the square on the bottom? I can take a square root. Got to be careful. It's got to be all on its own. Maybe we should rewrite it. 0.0184 equals x. 1.0 minus 2x. Both of them are squared. That's all squared. There's our perfect square. Right there. Okay? Square root. Square root. If someone could give me that number square rooted to an extra decimal, or an extra significant digit, means I need 4 significant digits. Actually, you know what? We've only got 2 significant digits in the question, don't we? Is that correct? We only got 2 significant digits in the question? Yeah, so 3 is good, because we're going to round back to 2 and we're done. You should always keep an extra significant digit so you can round one back when you do a calculation. So if you do a calculation midway, keep an extra digit. You got a number for that? 0.136. That's the square root of 0.01. Okay, good. And then that gets us x over 1.0 minus 2x. And now we're solving for x. We're doing our math. That's going up to the side there. I'm going to just write on this side here. So what have I got? 0.136 times 1.0 minus 2x equals x. So foiling that thing through, 0.136, and that's times 1, minus 0.136 times 2. That's going to be what? 272? Sorry? 272? So 0.272x equals x. 0.136 equals x plus 0.272x, which is, and I'm not doing it this time, 1x plus 0.272x is equal to 1.272x, 0.136. Divide off 1.272, divide off 1.272, and x is equal to. Yeah, what do you got? 0.8. What? I need the big cone. 0.11. Speak up! Oh my goodness! There's a machine here. It's humming. Can you hear it? So loud. 0.11. 0.11. 0.11. My wife tells me I should get my hearing checked. She's wrong. Okay. I don't want to hear half of it, so why would I? Okay, anyway. So now, we just have to substitute back in. So H2 1.0 times, I'm out of room here. I need you guys to help me. HI is 1.1, concentration, concentration HI, what is that? 1.0, what was it, minus 2x, right? 1.0 minus 2 times 0.11. And concentration of H2, I believe, equals the concentration of I2, which I believe is equal to just X, which therefore is equal to 0.11 moles per liter. Once you put in that final statement, all right, bring your unit back in, okay? And what is that mathematically? Somebody got that number? I'm not taking Catherine's answer. She's like miles away. I'll never hear it. What do you got? 0.78 moles per liter. Okay. All right. And I do have some homework questions that are on the slide. And there they are there. And yeah, that's obviously where we're going to stop. Just looking at our little summary here. So number 4, starting, not at, but with initial conditions, all right? So that's what these questions are all deal with, starting at initial conditions. And the first one we did was perfect square problems, okay? And for all of these, starting with I, you'll be given all I, right? And K. And we must, yes, use ice all the time with that one. Okay? And in a perfect square situation, you will always end up with K being equal to, and it'll be something, 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 something over something, 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 something. And it's always going to be squared, squared, right? Actually, I'll give you a heads up. Or, because you're going to get an assignment on doing a bunch of these, as you might imagine. These are quite a long, elongated thing, and I will give you some problems on a test, obviously. But if I'm giving you anything that is algebraically complex, if I give it to you on a test, you'll be doing algebra forever, right? So I'm going to give you an assignment. But it could be something like this. You could also have something, something, something over something, 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 right? And you could have 4th n squared, because you could take the square root of that as well, get rid of the square, and that becomes a 2, right? So you could have any scenario like that. Yeah. So be aware of that. And then you can take the square root, right? And then take the square root. I think you get the idea. Yep. Yeah, there's some that you could have to take a cube root, but that's going to come in the solubility ones. I don't give you cube root ones in just the introduction to equilibrium. Yeah. Okay. All right. So there is a good place to end because I'm running out of time.